The Hobart Flower Swarm Metabolism, a comprehensive framework for planetary harvesting and system-level mass integration. Abstract. This treatise details the operational architecture, thermodynamic mechanics, and structural dynamics of the Hobart Flower Swarm, a late-generation, modular planetary ingestion system designed for high-efficiency mass reclamation. The system utilizes universal, mile-diameter dodecahedral units configured into specialized orbital geometries to execute multi-phase planetary digestion. By integrating orbital solar mirror arrays, atmospheric pneumatic suction conduits, and resonant tidal dissipation, the Hobart Flower Swarm systematically strips volatiles, liquefies solid lithospheres, and collects ionized planetary mass to fuel stellar propulsion systems and mega-engineering projects. Volume 1. Structural Morphology of the Universal Dodecahedral Unit. The primary foundation of the Hobart Flower Swarm rests upon a single, scalable structural node, the Universal Dodecahedral Unit. Measuring precisely 1 mile in diameter, each node is constructed from high-tensile, heat-resistant composite lattice structures designed to withstand extreme gravitational shearing and thermal stress. The 12-sided geometric profile provides an optimal balance between structural volume, omnidirectional surface mounting, and modular interlocking efficiency. Mobility and stabilization are governed by two internal primary systems: high-impulse omnidirectional fusion jets and heavy-duty internal flywheel stabilization assemblies. The fusion jets provide fine attitude control, precise orbital positioning, and rapid translational movement during formation changes. The flywheel stabilization arrays allow each mile-wide node to manage massive rotational momentum, counteract external torque during fluid drag or tidal interactions, and maintain precise orientation relative to adjacent units. For thermal energy reception, each unit is equipped with retractable reflective sheets deployed from structural housing bays along its exterior frame. When extended, these high reflectivity sails act as focused energy collectors, absorbing and redirecting concentrated stellar photons transmitted from the orbital mirror fleet directly into internal power converters and directional propulsion systems. Volume 2. The Parabolic Mirror Array and Stellar Power Transmission. The continuous energy budget required to process an entire world exceeds localized energy storage capacity. Energy delivery is sustained by an orbital mirror fleet sailing in a continuous parabolic arc around the host star, looping around the target planet, and returning along a precise gravitational trajectory. This parabolic mirror loop acts as a high-density photon highway. The mirror sails capture raw solar radiation near the host star, concentrating the light into coherent, high-flux beams that are focused directly onto the swarm working around the target planet. As the power-bearing light strikes the retractable reflection sheets of the dodecahedral units, it is converted into electrical, thermal, and kinetic energy. This continuous power relay eliminates the need for heavy internal fuel reserves within the swarm nodes, allowing the universal units to allocate their internal volume primarily to storage reservoirs, fluid channels, and field generators. The solar array ensures that as the target planet undergoes intense structural breakdown, the energy input to the swarm remains constant and fully controlled. Volume 3. Atmospheric Boiling and Pressurization Mechanics. Before the solid lithosphere can be harvested, the planetary atmosphere must be stripped. To maximize the efficiency of atmospheric extraction, the target planet's oceans are intentionally vaporized in place using focused light from the parabolic mirror array. Concentrated beams of solar energy are directed at the planet's water bodies, raising surface water temperatures past the boiling point across entire oceanic basins. As the liquid water transforms into superheated steam, it expands rapidly into the lower troposphere. This continuous phase change dramatically increases localized and global atmospheric pressure. Maintaining high atmospheric pressure prevents the gaseous envelope from dissipating prematurely into space and ensures a dense, high-energy working fluid for the extraction conduits. By artificially boosting atmospheric density through ocean boiling, the swarm guarantees a continuous, high-mass flow environment at the intake point of its extraction machinery. Volume 4. The Ribbon Architecture and Atmospheric Skimming. With the atmosphere superheated and pressurized, the swarm shifts from an open orbital cloud into a tightly bound equatorial structure known as the ribbon. The ribbon remains in a stable orbital regime above the drag-heavy layers of the planet, allowing the individual units to maintain orbital velocity without decaying into the planet's gravity well. From the ventral side of the ribbon, vertical extraction assemblies descend into the dense atmospheric layers. To prevent these descending conduits from flailing, bending, or suffering structural failure due to atmospheric turbulence and planetary rotation, the siphon tubes are enclosed within a rigid structural ring. This outer ring acts as an aerodynamic slicing wedge, cutting through high-speed winds and stabilizing the central fluid channels. The wedge assembly is modularly built from the ribbon down as it descends, with the outer skin sliding along structural tracks to continually extend the assembly until the bottom mouth reaches the designated atmospheric density layer. Volume 5. Lung Action Pneumatic Siphoning Dynamics. The extraction of the pressurized atmosphere operates via a cyclic mechanism termed lung action siphoning. Rather than relying solely on high-energy static suction pumps, the swarm uses the physical structure of the enclosed siphon tubes to establish a planetary-scale pneumatic diaphragm. The structural wedge slides along the atmospheric boundary while nested chains of dodecahedral units lower themselves inside the tube. Once the lower mouth of the conduit is immersed in the superheated steam and gas, the upper units near the ribbon execute a rapid, coordinated volumetric expansion. This sudden expansion creates a massive drop in internal pressure within the upper tube relative to the extreme ambient pressure at the lower mouth. The planet's own atmospheric pressure violently forces superheated steam and gases upward through the conduit, driving the fluid into the awaiting collection chambers of the ribbon. By repeating this rhythmic expansion and contraction, the swarm draws out the atmosphere in continuous, high-volume breaths. Volume 6. Dynamic Unit Replacement and Reservoir Fluid Distribution. As superheated gas and vapor stream upward through the siphon tubes at extreme velocities, the kinetic force and buoyancy of the current are harnessed to drive the swarm's internal logistical cycle. The upward fluid drag pulls the individual dodecahedral units lining the interior of the tubes upward toward the ribbon frame. This continuous upward motion creates an automated fluid and material exchange loop. As a unit moves up through the conduit, its internal storage reservoirs are filled with dense, compressed atmospheric gases and condensed water vapor. Upon reaching the top of the tube at the main ribbon, the full unit transfers its stored fluid to adjacent empty units along the orbital ring through passive pressure equalization valves. Once its reservoirs are emptied across its neighboring nodes, the structural unit is cycled back down the outer framework of the wedge assembly to replace an incoming unit at the base of the tube. This continuous mechanical carousel ensures that structural elements are constantly refreshed, thermal loads are distributed evenly across millions of nodes, and harvested mass is seamlessly pushed into the outer orbital storage network. Volume 7. Transition Mechanics. Atmospheric Evacuation to Resonance Ring. Once the atmospheric pressure drops below the threshold required for efficient lung action siphoning, the swarm initiates a complete structural reorientation. The ribbon unlocks its vertical wedge conduits, retracts the dodecahedral units back into the primary orbital plane, and disassembles the siphon assemblies. The universal units shift from a tight equatorial ribbon into a wide, counter-rotating ring formation that completely circles the target planet. Because all units share a universal design, no specialized retooling is required. Every unit that previously served as a component of the pneumatic lung now functions as an orbital mass anchor and field transmitter. The counter-rotating ring adjusts its orbital parameters, establishing a dense, high-velocity band of mass that orbits in the direction opposite to the planet's rotation. This counter-rotation maximizes relative velocity differences, preparing the system to apply continuous, fluctuating gravitational forces to the solid planet below. Volume 8. Gravitational Tidal Dissipation and Radial Oscillation. With the counter-rotating ring in place, the swarm begins its second primary phase, planetary liquefaction via gravitational tidal dissipation. The mass of the swarm ring, powered and stabilized by the parabolic solar mirrors, is equivalent to or greater than a significant fraction of the planet's total mass. The units within the ring begin a coordinated, rapid radial oscillation, surging inward toward the planet's surface and retreating outward in precise wave patterns. This physical oscillation causes severe, rapidly changing gravitational gradients across the planet's surface and interior. The differential gravitational forces stretch the target planet along the axis of alignment and compress it at the sides. As the ring rapidly shifts its mass back and forth, the planet's mantle and core are subjected to violent, continuous mechanical flexing. The immense internal friction generated by rock strata sliding against rock strata converts gravitational kinetic energy directly into thermal energy throughout the planet's interior. Volume 9. Resonant Frequency Matching and Mantle Liquefaction. To accelerate the thermal conversion process, the radial oscillations of the swarm ring are tuned to match the natural mechanical resonance of the target planet. By driving gravitational pulses at the fundamental acoustic and seismic frequencies of the world, constructive wave interference is established within the interior. These resonant standing waves stack inside the mantle, building immense pressure fronts that shatter the rigid crust from the inside out. Within a short period, the planet's core and mantle melt completely into a continuous, churning sea of liquid magma. As the internal temperature continues to surge past the melting point of silicate rocks and metals, the entire world transforms into an expanded, superheated liquid sphere. The crust ceases to exist as a solid boundary, leaving a churning, low-viscosity molten body held together only by its immediate gravity and the surrounding field forces of the swarm. Volume 10. Superheating, Surface Wave Stacking, and Ejection Dynamics. Once the planet is fully molten, the swarm intensifies its resonant oscillations to drive the liquid surface past its boiling point, preparing the solid mass for spatial ejection. The radial wave pulses create massive, standing liquid waves that travel across the planetary equator. Where these resonant waves intersect, constructive interference produces extreme crest points that rise thousands of miles above the nominal surface level. Simultaneously, focused thermal energy from the parabolic mirror array continues to blast these wave crests, heating the liquid silicate and iron until it undergoes rapid vaporization. At peak resonance amplitude, the vertical velocity of these molten wave crests exceeds the local escape velocity of the planet. Combined with the upward gravitational pull exerted by the close proximity swarm ring, huge globs of liquid rock and ionized silicate vapors are sloshed off the surface directly into space in targeted, predictable trajectories. Volume 11. Electromagnetic Netting and Mass Capture. As molten globs and superheated gas plumes erupt off the planet, they enter the immediate operational zone of the oscillating swarm ring. Due to extreme thermal ionization, the ejected silicate and metallic material carries a significant net electrical charge. The interlocked dodecahedral units in the ring deploy strong, coordinated magnetic and hydrodynamic fields, creating a high-density electromagnetic net spanning the orbital paths around the planet. This field net catches the incoming high-velocity molten material, decelerating it through magnetic braking and preventing it from scattering into unrecoverable orbits. Once captured by the field net, the liquid mass is directed into the collection funnels of the nearest swarm nodes. Internal cooling channels within the units rapidly solidify the rock and metal, channeling the refined mass into storage reservoirs or converting it directly into dense structural fuel blocks for transport. Volume 12. Material Processing, Isotope Fractionation, and Fuel Refining. The harvested planetary mass is immediately processed within the internal chambers of the dodecahedral units. Because the material enters the swarm in superheated, ionized states, elemental and isotopic separation can be executed with high chemical efficiency. Centrifugal collectors and electromagnetic mass spectrometers inside the nodes separate heavy industrial metals such as iron, nickel, and titanium from lighter silicates and volatile elements. Hydrogen, oxygen, and carbon harvested during the atmospheric lung phase are stored separately in high-pressure cryogenic reserves. Valuable isotopes, particularly deuterium and helium-3 extracted from the superheated water vapor and mantle gases, are diverted directly into the fusion power plants of the swarm nodes. This continuous fuel replenishment ensures that the swarm remains energy positive throughout the entire planetary digestion cycle. Volume 13. System Momentum Conservation and Stellar Engine Integration. The ultimate objective of the Hobart flower swarm metabolism extends beyond localized material harvesting. It provides the mass and momentum required to construct and operate system-scale stellar propulsion systems. Stars contain the vast majority of a solar system's total mass, but the orbiting planets contain the majority of its angular momentum. By systematically digesting the planets, the swarm captures both high-density reaction mass and concentrated angular momentum. The refined metals and dense silicates extracted from the target world are funneled into the construction of massive stellar thrusters, such as Kaplan engines or direct radiation sails, built around the host star. The processed planetary mass serves as the physical reaction propellant that these engines expend to move the host star through interstellar space. Volume 14. Ecological Cycle of the Swarm and Post-Harvest Dispersal. Upon the complete depletion and ingestion of the target planet, the local gravitational well vanishes, leaving a clear orbital path around the host star. The Hobart flower swarm enters its post-harvest logistical phase. The universal dodecahedral units disengage their tight structural ring bonds and expand into a distributed, low-density fleet profile. Using their internal fusion jets and high-efficiency solar photon sails, the units redistribute their stored mass across the broader fleet network, filling empty storage nodes and repairing structural wear sustained during the high-stress digestion process. If additional planetary bodies remain within the star system, the swarm reforms into its ribbon configuration around the next target world, repeating the atmospheric lung extraction and gravitational resonance cycles. If the system is fully harvested, the swarm links directly with the stellar engine infrastructure, using the star's energy to propel the entire system toward its interstellar destination. Volume 15. Theoretical Limits and Operational Summary. The Hobart flower swarm metabolism represents an optimal synthesis of planetary engineering, fluid dynamics, and resonant gravitational physics. By replacing specialized, single-purpose machinery with universal, mile-diameter dodecahedral units, the system achieves maximum adaptability across all phases of planetary digestion. Through the synchronized deployment of parabolic solar mirrors, pneumatic lung action atmospheric conduits, and counter-rotating resonant rings, the swarm bypasses traditional brute force mass extraction methods. It forces the target planet's own thermal, atmospheric, and structural inertia to assist in its own dismantling. The result is a clean, continuous closed-loop metabolic cycle that converts intact planets into refined structural materials, specialized fusion fuels, and stellar reaction mass, cementing the Hobart flower swarm as an efficient architectural model for late-stage stellar ecosystem management.